Hello everybody, welcome to part 2 in the 3-part series of looking at hardened concrete properties. Drying shrinkage is an important contribution to the durability of concrete. Concrete's like a sponge, and it's a solid with a lot of small pores inside. You're like, man, concrete doesn't look like a sponge to me. Well, the pores are just smaller than the sponges you're used to dealing with. And it's not all soft and spongy. It's hard and it'll hurt you, right? But believe it or not, it's like a sponge. It's got a bunch of small pores inside of it. And when you lose water inside those pores, the concrete will shrink. Yeah. It'll change shape. For example, I've got a beam here that's wet and a beam here that I call dry. And if I measured the length of the first beam and I compared it to the length of the second beam, I'll actually find the length of the first is greater than the length of the second. Whoa, pretty crazy, huh? And I can measure something called shrinkage. Shrinkage would be the change in the lengths over the original length. And this is typically somewhere between 300 microstrains and 500 microstrains. That's typical ballpark numbers for ultimate shrinkage for concrete. So why do people care about this? Well, when concrete shrinks, if it's restrained, that means if it's held back, then it'll gain stresses and it can cause it to crack. There's a lot of cracks that you'll see in concrete all over that are at least partially contributed to by this shrinkage. So if we can make concrete that would shrink less, that means it might crack less. Well, I said might because there's a lot of stuff that goes into actually determining if something's going to crack or not. I'll talk about that in just a second. The way to measure this shrinkage, the way to measure this length change, is that people actually embed metal pins into the concrete when they're making it. Yeah, the pin is going to go a little bit into the concrete and a little bit out of the concrete. So if it changes length, you're going to be able to measure it. You can also commonly measure the weight change over time. And this length change is measured with a device called a comparator. It's an LVDT. You're like, what's that? Well, it's a deflection gauge. It measures movement, basically. And it's on a stand or a frame. And you make your comparisons to a rod of a fixed length made out of a material called Invar. What? Yeah, Invar. Invar is a metal that won't change much with change in temperature. The coefficient of thermal expansion, that's the amount of movement that happens for a given amount of temperature, is very low for Invar. So what you do is you have this frame, you put in your Invar bar, just a piece of metal, you have your little measuring device at the top, and you zero your gauge. That's zero. That's the initial. Then you put your concrete in, and you measure it, and you say, what's the length? And you compare that length to how it changes over time, and that will tell you how much it strains. Pretty cool, huh? So this test is not run by everybody. There's some challenges with it. One, there's no standard way to cure the concrete. That's curing. That's when you protect the concrete. It's when you provide moisture, and you usually provide moisture. At least you provide a way not to lose moisture. And usually you provide a way not to lose or change temperatures drastically either. That's what curing is all about. So there's no standard way to cure the concrete, and the curing is definitely going to have an impact on the results. And there's early age shrinkage, very early age shrinkage that can occur in the first 24 hours, typically called autogenous shrinkage and chemical shrinkage. We'll talk more about those coming up. But this test doesn't measure it because in the first 24 hours, the sample is still in the molds, okay? So you can't use those pins to measure the length because it's still inside the steel molds. The samples also have to be stored in a very unique temperature and humidity. Typically 73 degrees Fahrenheit and 50% relative humidity, typically. So you have to have a specialized room or facility. And it can take around 14 to 28 days to get meaningful results out of the test. That's a long time. And this ultimate shrinkage, the ultimate shrinkage that it's going to get to, isn't reached until about 6 months. And this is a long time. What I'm trying to say is that if you were to plot shrinkage versus time, what you'll find is that it goes like this. And to get flat, it may take 6 months. It may take 9 months, depending on the quality of your concrete. But you can't get anything useful until around 14 to 28 days. And then you're comparing the early parts of the curve. But that's what people do sometimes because they don't want to wait for 6 months. Also, this doesn't measure cracking. This measures shrinkage, which happens to be one component of the drying shrink or the cracking caused by drying shrinkage. So it doesn't really get at what you want, what's important. And people are working on other tests to go after cracking, but they really haven't seen widespread adoption. People have used them in the lab, research groups have used them, but not a lot of practitioners are using them in their everyday job. That's going to be something to watch out for, and that's going to be an opportunity for those that come up with something useful. Thanks.